Hey, Christina.
Hey, Susan.
Let's talk about the central limit theorem.
Okay. Central limit theorem. Okay.
Okay.
I don't know how to spell theorem. Is that right?
I think so.
Okay,
I think
cool.
you did it very well.
Good. So I think that we should start from an example and then get into the more formal definition later.
Okay.
Okay. So let's consider this graph here. I've got curve A and curve B. ACT scores for high school seniors at a large school district are normally distributed. Okay, notice my bell curves, right?
Okay.
With a mean of 22 and a standard deviation of 4.
Okay.
Compare the two distribution curves given below. So, curve A, every student is represented on the curve as an individual and the entire population is represented.
So this is like a normal distribution of the whole population of students who've taken the ACT.
Yep, my population that has a mean of 22 and a standard deviation of 4.
Okay.
Okay. So, that's curve A. Curve B, groups of 25 students are randomly selected from the population, so say classes of 25 students, and the mean ACT of each group is represented on the curve.
Oh, so wait. We're taking 25 students, taking their all 25 ACT scores and averaging them together, finding the mean of the 25. Okay.
And then plotting that mean on a curve.
And doing it over and over and over again
Yes.
and making a bell curve from that.
Yes.
Okay, so one of them is a bell curve of populations, of the population, and one of them is a bell curve of a whole bunch of samples of 25.
So individuals, curve A is individuals from the population,
Okay,
and curve B are means of samples from the population.
okay. Okay, well, I'm looking at those two curves, and there's some significant differences between those curves.
Yeah, so specifically, what do we notice about the mean and the standard deviation for each of the curves?
Well, I'm looking at the mean, and if we put a dot at the top of the curve where the mean, or do that, it looks like the mean's the same for both of them.
Yeah, it does look like the mean is the same for both of them.
Looks like it's 22 for both of them. Wasn't that the mean? 22?
Yeah. What about the standard deviation?
Oh, there's a big difference there in the spread
Yes.
of the distribution.
Yes.
Curve A, which is the population one, is much more spread out
Yeah.
than curve B, which is those means of those samples of 25.
Yeah. The curve B looks like they're all bunched up a lot closer to the mean.
You know what? That makes sense.
Yeah.
Don't you think that makes sense? That the average of every sample is going to be pretty close to the average of the population.
Yeah, and so since it's less spread out, I would say that it has a smaller standard deviation, right?
Yeah.
Okay.
Yeah, so B has a smaller standard deviation than A.
Yes. Now what the central limit theorem tells us is that specifically I can figure out what that standard deviation is.
Okay, so if I know maybe the population standard deviation, which is what, 4?
Yes.
And what else am I going to need to know besides the 4?
Well, it depends what size samples I take.
We were taking samples of 25, right?
Yes.
So the two pieces of information I need to know are the population standard deviation
Yes.
and the sample size.
Yes.
Okay.
Yep. And so let's actually calculate what that would be. Okay. Okay. So my curve A here, that's representing individuals in the population, had a mean of 22 and a standard deviation of 4.
Yes.
Okay. Curve B, okay, this is a sampling distribution of sample means.
So we're going to put a little symbol there to remind us that it was sample means, which X bar is sample mean. So it's just kind of a little note there, a little footnote.
Yep. And we said that they have the same mean.
Okay.
And that's true. That's part of the theorem.
Yes.
Okay. Now, the standard error, which is the name that we give the standard deviation of the sampling distribution. Okay, it's smaller because I actually take that population standard deviation, sigma, and divide it by the square root of n.
Okay, we can do that because we've got both numbers.
Yeah, so in our situation, sigma was 4, and our sample size was 25. We were taking groups of 25.
Square root of 25 is 5. So 4 divided by 5 is 0.8.
Yeah.
So that's a big difference in the standard deviations between the two.
Yes.
So both of them have the same mean, but one of them has a standard deviation of 4 and one of them has a standard deviation of 0.8.
Yep, exactly. And we call that standard deviation that we've adjusted, that we've divided by the square root of the sample size. That's called the standard error.
Got it.
Okay?
Okay.
Awesome. So you're going to do an example like that in your quiz, and I think that's it.
Yep.